podocyte, depending on the cumulative dose. And after those years, endothelial cells were cleared in all patients. So it is an issue with podocytes, long-lived cells sitting outside the capillaries that are more difficult to clear. And it is precisely podocyte injury which causes proteinuria. And proteinuria, the main risk factor for losing glomerular filtration rate in Fabry patients. So we had some insight that those may be important. And we had further data regarding those from something that happened 8 years ago, which we now call the shortage. The shortage was triggered by a viral contamination of the enzymes production facility. So they could no longer produce enough enzyme for all Fabry patients in the world. So many patients had to switch enzymes or had to lower the enzyme dose. And this went on for several years. And this was a tragedy, but we could learn from it. There are a number of reports that describe what happened during the shortage and after the shortage, when patients were involuntarily underwent dose reduction. And well, you may find many reports there. Some reports deal with a few patients, but I think you may get the best information when you look at large reports. And this is the largest report to date. And it does not represent only what happened over a few months, but over 2 years. And in this report, nearly 100 patients in Germany, they were on araxidase beta, 1 mg per kg at baseline, and then the shortage sheet line, the only patients that had preservation of glomerular filtration rate over those 2 years were the ones on araxidase beta 1 mg per kg. And the other two groups that underwent a dose reduction or switch to an enzyme with an approved, with a labeled lower dose, they lost renal function within these 2 years. And moreover, when they looked at a score on severity, the global severity of the disease, they observed that it increased in patients who had dose reduction or switch. But you may think, okay, but you know, children, they have accumulated lower amount of deposits, they have less severe disease. So maybe we can use lower dose and still get a good therapeutic response. And there's also a report coming out of the shortage. This is the same Norway group that I mentioned before, that they are performing repeat biopsies. So they assessed podocyte deposits, and this is what they saw for 3 children that underwent from 3 to 4 renal biopsies. So at baseline, all of the children had huge amount of deposits in podocytes. After 5 years of ERT, the amount of deposits went down, but then they underwent a 3rd renal biopsy 3 years later, and deposits were back. What was the therapeutic correlation of these findings, of this observation? What we can see here for the 3 patients, what the dose of ERT. So initially they were on 1 mg per kg ERT, but after the shortage, the dose was reduced to somewhere around 0.2 mg per kg. And it was after these 3 years on 0.2 mg per kg that deposits came back. A single boy, he underwent a 4th renal biopsy. And we can see the details here. So at baseline, deposits in podocytes, after 5 years on 1 mg per kg, deposits cleared. 3 years on lower dose, deposits increased again. Couple of years on higher dose, deposits disappeared again. So there is a dose response even for children, apparently, as we can understand from this report. But what about hard outcomes? Patients are not so concerned about podocyte deposits. They may not even know what's a podocyte. but they do know what means dialysis, or death, or heart failure, or stroke. So do we have data on enzyme replacement therapy and these hardened points? There is a clinical trial, phase 4 clinical trial, 82 adults who already had at baseline, they have renal disease, so they have pretty advanced Fabry disease, and they were randomized to placebo or to agalsidase beta 1 mg per kg every 2 weeks. And patients on placebo, they had more severe clinical events of the ones we have mentioned than patients on agalsidase beta. And this was the case, despite the fact that patients on agalsidase beta, this was a large trial by Fabry disease standards, a very small trial by the standards usually ascribed to the assessment of hardened points. Statin trials, they followed 10,000 patients for 5 years. And here we followed, they followed 80 patients, so it was unbalanced at baseline. And patients assigned to agalsidase beta, they were older, and they were higher, they had higher proteinuria, they were at higher risk of progression, and despite this, there were less events. But then we also have registries. So authorities requested the companies to have registries so as to assess the effect of therapy in the real world and for many patients. And we analyzed the Fabry registry. And what you see here is the survival without severe events for 2 cohorts. In blue, patients who, when they started therapy, they had not had any severe event prior to therapy. And in red, patients that had had a severe event prior to therapy. So these were patients with more advanced disease. And look at the first 6 months. I cannot. Look at the first 6 months. Within the first 6 months, events are occurring, at a quite fast rate. But then there is a change of slope. After 6 months, the slope changes, and events occur at a lower rate. So we try to put some numbers of this on this. And these are the results. So these were all patients that started at 1 mg per kg agalsidase beta in the Fabry registry. Over 1,000 patients. This is the largest study reported to date. Median age at the start of ERT, 40 years. Remember, this is the median age when patients need dialysis, so this was quite advanced disease at baseline. And as it was a quite advanced disease, during the first 6 months of therapy, patients did have events. However, the interesting thing is that in the next 6 months, second year, third year, fourth year, and 5th year, the incidence rate of events was halved. This is what was observed. When you increase the follow-up, the number of events decreases. But these patients are getting older. If they were 40 years old at baseline, 5 years later they were 45 years old. So maybe we may have expected that the incidence of events may have been increasing if the main risk factor for having a heart event, a stroke, is aging for Fabry patients and also for us. And in Fabry disease, this was studied. And the upper line is male Fabry patients. And it was shown that when they age from 40 to 45, the incidence rate of a stroke increases. So indeed, we should have expected an increase in the incidence rate of events, but we observed a 50% decrease. And this was also true for the higher risk populations. For example, patients who, before starting ERT, they had already had a severe clinical event. So these patients were at higher risk of a second event. But after 6 months of therapy, what was observed was a decrease in the incidence rate of events. Male patients, older patients usually have a more severe disease. The disease is progressing with aging. These patients also benefited from agalsidase beta therapy. And finally, males. This is an X-linked disease. Males usually have a more severe disease. And also in males, this was observed, a decreased, a lower incidence rate of events after the first 6 months of therapy. And of course, this was also true for patients without a pre-ERT event, younger patients, and females. So this data support the concept that for most Fabry patients, there is not such a thing as too late in Fabry disease. So the patient had already had an event. You start therapy, and the incidence rate of events is lower. You may say, oh, while on therapy, my patient had a stroke. Therapy failed. But do we think in those terms for statins, for example? A patient on the statins has a myocardial infarction. Do we think therapy failed and we should stop therapy? And we should think, or we think statins only reduce the risk. They do not completely prevent. So if patients have a myocardial infarction while on statins, we do not stop the statins. We may even increase the dose because we know we are talking about risks. It's not an absolute yes or no. And finally, how to monitor therapy. Juan already mentioned lyso-Gb3, and lyso-Gb3 should be, the concept of lyso-Gb3 is a failed escape attempt. You know that sometimes in life we are in a difficult situation, so we make decisions in order to escape from this difficult situation, and then we end up in an even more difficult situation. This was the case, for example, for this inmate at a prison. He tried to escape from prison, and he ended up in an even worse situation. And you see the guards laughing at him. So for lyso-Gb3, we should think of it in those terms. So in Fabry disease, we accumulate Gb3. Gb3 is being accumulated. And from Gb3, lyso-Gb3 is generated by an enzyme which is called acid-ceramidase. So this is the escape route by which the organism tries to prevent accumulation of Gb3. And this occurs at the lysosome. But the problem is that lyso-Gb3 is more toxic than Gb3. This occurs within the lysosome. So when we measure lyso-Gb3 in the circulation, maybe in the cell, levels are even higher because it is thought to be generated within the cell. Okay, so lyso-Gb3 is correlated with the severity disease. This report observed both in males and in females a relationship between the amounts, the concentration of lyso-Gb3 in the circulation and the severity of heart disease. Lyso-Gb3 also decreases in response to enzyme replacement therapy. And in this report, there was a relationship between the decrease of lyso-Gb3 and the response of the heart to enzyme replacement therapy. So it has been associated with the degree of organ response. And it was also observed that it is sensitive to changes in the dose or in the enzyme. In this report, patients at baseline on agalsidase beta 1 mg/kg were assessed 1 year after switching to agalsidase alpha 0.2 mg/kg, and lyso-Gb3 increased. And as Juan mentioned before, lyso-Gb3 is thought to be pathogenic. At our lab, we have explored the effects of lyso-Gb3 on podocytes, culture podocytes. And the podocytes display a stress response to lyso-Gb3. So you culture the podocytes with the same lyso-Gb3 amounts that you find in the blood of Fabry patients, and the response is similar to the response of podocytes to high glucose levels. So there is an activation of inflammation, activation of the inflammatory response, secretion of TGF-beta1 that in an autocrine fashion promotes the secretion of extracellular matrix, promotes fibrosis, and there is expression of genes that are involved in the de-differentiation of cells. So lyso-Gb3 may be pathogenic. Lyso-Gb3 is responsive to enzyme replacement therapy. And now I'm showing this. I don't know whether you recognize it, this linear pattern of anti-GBM antibodies. And this is what you can find in Alport patients when they get a kidney transplant. Alport patients are missing GBM type 4 collagen. So when they get a new kidney, which is normal, which has GBM type 4 collagen, they may recognize this new normal type 4 collagen as strange. Their immune system had not been exposed to type 4 collagen before. So they reject it. They develop antibodies to type 4 collagen, and they may get these linear deposits in the GBM. And this is a very well-known phenomenon. When some patients with a genetic disease lacks a protein, and then the protein is introduced, you may develop antibodies. And this may also be the case with Fabry disease. So you may develop IgG antibodies against agalsidase. And Fabry disease can occur in males and in females, but the good news is that in females usually do not develop antibodies against agalsidase when you inject agalsidase intravenously. And this is also the case for males who have enzyme expression. So if the genetic defect allows the production of a protein, of an enzyme, and the immune system recognizes as own the enzyme from birth, there is usually no problem with antibodies. However, the bad news, male patients with no protein, with a severe mutation that prevents the production of the protein, the immune system has not been exposed to the protein, they may develop antibodies against agalsidase. It may be, there are reports of the development of antibodies in patients treated with either alpha or beta, and when antibodies do develop, they are cross-reactive with alpha or beta because they share the same amino acid sequence. So should you be concerned if your patient develops antibodies? There was a paper that addressed this question, and it's not in any population, but in the population that was enrolled in placebo-controlled clinical trials and in the extension study. So this was a very well-followed population. And they followed anti-alpha-galactosidase IgG antibodies, and they observed no correlation with onset of clinical events, rate of change of EGFR, or abnormal elevation of GL3. There was, however, some association with anti-enzyme antibodies and persistence of glycolipid deposits in the endothelial cells. So it is true that it is no good if your patient develops antibodies. What can you do about that? There are some reports that provide some insights. For example, this is a report from the Netherlands. They represent urinary GL3 at baseline, and you see how it decreases after the start of ERT. Some patients received 0.2 mg per kg ERT, and some patients 1.0. And some patients developed antibodies in red, and some didn't in black. And the patients who developed antibodies, there was a trend towards increasing GL3 in the urine. But this was much less in patients on higher dose than in patients on lower dose. So maybe if your patient develops antibodies, those may be important in order to decrease the negative effect of the antibodies. And we have this other publication originated for patients who were switched from agalsidase alpha 0.2 mg per kg every 2 weeks to agalsidase beta 1 mg per kg. And we see that after switching to an agalsidase formulation, which implies a higher dose, lyso-Gb3 levels, and this is lyso-Gb3, the glycolipid that is injurious, were decreased. And this was also the case, and mainly the case, more evident the case for patients who had antibodies. So if your patient has antibodies, he may benefit from switching to a higher dose or to an enzyme formulation that associates a higher dose. And this is the take-home message. So where is Fabry disease? It may be just in front of you. One of your hemodialysis patients may have Fabry disease. You should learn to look up and recognize the etiology, because this may benefit the patient, but also the patient family. How to treat Fabry disease, the current standard throughout most of the world is enzyme replacement therapy, and doses should be individualized and optimized in order to halt progression. Podocytes should be immortal, but they are not, and published data suggests that ERT may clear them in a dose-dependent manner. We have learned from the shortage, and we have learned that at least in some patients, if the dose is reduced, the progression is higher. And with long-term follow-up of agalsidase beta patients at 1 mg per kg in registries, over 1,000 patients, there was a signal towards decreased incidence of severe clinical events at this dose. How to monitor therapy? You may biopsy patients that the people in Norway are doing. You may follow up proteinuria or GFR, but this is too late. You are interested in how the enzyme is clearing the deposits. And currently, the best standard we have is lyso-Gb3. Thank you very much for your attention. I think we have 5 minutes left. If there is any question from the floor, we may attend it, and if not, we... Yes?
Thank you for your excellent talks, both excellent talks. The question is about in switch patients from the agalsidase beta for agalsidase alpha. There are increase on lyso-Gb3. It's only in observational studies. Well, what is the clinical implications of this increase? There are clinical implications, or only is observational implications in these patients, in switch patients?
So, the question is about randomized clinical trials versus observational studies?
Yes. Yeah, the clinical implications of the increase of lyso-Gb3 in the switch patients from agalsidase beta to alpha.
Okay, so the clinical implications of the change of lyso-Gb3, we cannot know from these particular studies because they only looked at lyso-Gb3, but we can build up a whole picture when we have the data from animal studies showing that lyso-Gb3 is pathogenic, from observational studies where they observe this association between dose and lyso-Gb3 levels, and from clinical trials in which the only placebo-controlled clinical trial that looked at severe clinical events showed that they were decreased with 1 mg per kg every 2 weeks, and then with observational studies from the registries when a similar decrease in the incidence rate of events was observed with agalsidase beta 1 mg per kg.
Okay. Is unknown the clinical yet?
The clinical?
The clinical implication is unknown, desconocidas.
I don't understand. ¿Sí?
Yo creo, vamos a pasarlo al español. La pregunta es, si bien cuando yo cambio la dosis de terapia entre un grupo de pacientes, los paso, ¿sí?, de una dosis de 1 miligramo a 0,2, incremento el lyso-Gl3, ese incremento del lyso si representa también empeorías clínicas. Vos querés correlacionar el incremento del lyso con la presencia de peoría clínica. Eso es lo que quiere preguntar.
Más que la disminución que se observó desde 2009, el cambio de beta-alfa, ¿hubo alguna implicación clínica? ¿Hay implicaciones observacionales?
Sí, bueno, el mayor estudio publicado es el que he presentado, el alemán, y cuando los pacientes cambiaron a alfa 0.2 o disminuyeron la dosis, la enfermedad renal progresó, se perdió filtrado glomerular y aumentó el score de riesgo de MAINS, el score de enfermedad de MAINS de severidad, de gravedad de la enfermedad. O sea que sí hay una relación clínica.
¿Y en cambios, en switcheos?
¿Perdón?
En switcheos de beta-alfa existió incremento en lyso-Gb3. pero implicaciones clínicas desconocidas.
Ese artículo eran solo 15 pacientes. Yo creo que cuando quieres medir implicación clínica tienes que mirar la cohorte más larga, más grande que tengas, y en estos momentos es la de Würzburg, con 80 pacientes a 2 años, eran casi 100 pacientes de seguimiento de 1 año. Tanto a 1 año como 2 años vieron lo mismo, y es una repercusión clínica por los scores que se utilizan actualmente de gravedad con el MACE score.
Muchas
O sea que
gracias.
sí que hay una implicación clínica, sí, pero para eso, claro, no puedes comprobarlo en un solo paciente, tienes que estudiar una población grande.
Ok, gracias.
Muy bien, pues thank you very much for your attention.
what I've seen in another session was that the moderators went and sat there so they could see the slides.
It's 70s.
Oh,
Yeah.
I wonder why they went. Maybe it was a different setup.
They want you to stay here. This is what I have rehearsed for every session of 70s. When you moderate, like the plenaries, you have you rehearse like 15 minutes before. So I want you to sit here throughout. The slides are displayed here and others show.
We're aiming for 15 plus 5? Sure. It's good. There's no timer up there.
I know.
Presumably we know how to advance the slide.
Well, so this is, you can point with the mouse just only, and then you advance with this, and you'll have a timer on.
Oh, there is a timer?
Yeah, there is. Yeah.
So we'll start the session.
Shall we wait for
Yeah.
Oh no, it's not even time. We're next week.
There we have a minute. We can do it on Mexican time too.
Have to wait for like,
So wait till tomorrow.
yeah. Exactly. We have to turn the music on.
Roberta's had a good time.
Oh no, it's not because I don't know how to get rid of this. I messed up. Progression.
Good. So they turn the music off, the doors are closed.
Okay.
So they say tap on it.
Yeah. Good afternoon, everyone. We're going to start our session of CKD progression. My name is Magdalena Madero, and this is Dr. Andrew Levy. We're both going to be moderating the session, and we're going to start with our first speaker.
Great. So our first speaker is Dr. Joseph Korish. Dr. Korish is the Comstock Professor of Epidemiology, Biostatistics, and Medicine at the Johns Hopkins University Bloomberg School of Public Health. And I have the privilege of saying he's been a longtime collaborator, and I definitely look forward to hearing him speak about what is meaningful CKD progression.
All right. Thank you very much for the invitation and the wonderful meeting and my introduction to Mexico City, which has been lovely. So I think we all have a lot to cover and not too much time, but interesting topics. So basically my outline is to make sort of three main areas. Talk about the KDIGO CKD staging as the context. Talk about risk associated with eGFR change and albuminuria change as measures of progression of kidney disease, and then talk about some limitations. So in terms of the KDIGO guidelines, I think we're all familiar with the grid, right? And we need to take in mind that the CKD definition has not been changed since 2002, and CKD is defined as abnormalities of the kidney structure or function present for 3 or more months. In terms of staging, the staging has been updated to include the cause, the GFR category, and the albuminuria, so CGA. In many ways, elements of this were in the text all the way from 2002, but now explicitly cause and albuminuria are stages as well. So if we want to think about progression, what you can see in the KDIGO guidelines is that a decline in GFR category is considered progression. That makes sense. And then a certain drop is said to happen if there's at least a 25% drop in GFR. So if you move from a GFR of basically 46 to 44 and went from 3A to 3B, it's considered a decline, but not a certain decline because you may be waving around up and down. And a 25% drop was thought to be more substantial. I'll show you some of the data that's consistent with that and how that relates to 30%, which we've used for clinical trials. Then they talk about a rapid decline of a slope of 5 ml per minute per year or more. And we'll talk about the issue that the confidence in those conclusions depends on the number of years and the number of measures. So in many ways, 5 mLs per year is very rapid, and if you do that for 20 years, that's it. There is no more kidney function. On the other hand, if you do it for 1 year, it could be within the level of error of your measurements. So the number of years really makes a difference. And for albuminuria, we talk in the KDIGO guidelines that small fluctuations are common, but we don't really make a statement about how much of a change is a substantial change. And I think for that, we're beginning to make more progress in various research. Many people have published, and I'll show you that at least a 4-fold change in albuminuria is associated with a 3-fold change in risk, but I think there's more progress to be done. I'll show you a number of results. Most of them that I will present is from the Chronic Kidney Disease Prognosis Consortium. And I'm very fortunate that over 70 cohorts have entrusted their results to us to work together on data from about 10 million participants from throughout the globe to make conclusions. And I won't have much time to name the different cohorts and different collaborators, but really people have worked for decades and then entrusted their data to this group from general population cohorts, high-risk cohorts like diabetes and hypertension, and CKD cohorts to look at later stages of disease. So I think we've been able to come together and try and see where there's consensus in the data. So when we talk about progression, I think there's 2 different perspectives that are really important, and we've tried to elucidate that. This is in a summary paper by Dr. Levy, right? So the first is a clinical trials perspective. What it asks as a question is more rapid CKD progression in course B compared to A associated with higher subsequent risk of ESRD? And in many ways, over time, if GFR declines, you would think, of course, the person B is worse than A, and that's why GFR is sort of so useful in terms of looking at ESRD, right? But we want to show how much worse it is. The other thing that you might say is, well, it's a little silly. Shouldn't we be comparing a patient where I see them here at the last visit, they have the same GFR of 45, and I say, is patient B that progressed more rapidly in the past worse off than patient A who didn't progress at all, right? Both are valid questions. My main point is that we should not confuse the two. They're actually different questions. I'll mostly focus on the first one in that the first question allows you to say, well, if the patient moved this much, can I tell them this is worse, or can I say it's about the same? And then the next question is, when we get to that point, how about extrapolating into the future, which will be harder? So I'll show you some of those results. So we've analyzed the data in each participating cohort. We model the percent change in GFR using a spline. We meta-analyze across the cohorts, and we examine heterogeneity and look for consistency. And that's the good thing about a consortium, is you're actually looking for replication in science, not just one answer that differs from another answer. The question is there consistency across the globe's data? So to address this, we did this with a large number of collaborators, with 19 cohorts with GFR less than 60, 9 cohorts with GFR greater than 60. During a baseline period here, we'll focus on 2 years where we look for progression of kidney disease over 2 years, 3 serum creatinines, and subsequently a large number of ESRD events in the next 2 years. It actually will be interesting to see progression over the next decade, but that's going to be a lot harder. And then we adjusted for a good number of variables to show that the progression was predictive of risk independent of other variables. So this is our main result for progression of GFR. Basically, on the x-axis is the percent change in GFR. If we focus on the left side, it's for cohorts with kidney disease, GFR less than 60. On the right side, GFR greater than 60. Fortunately, when you look at percent change in GFR, the associations are actually remarkably similar. In red here is the previous standard for progression. We know that if someone's serum creatinine doubles, that is really a bad thing, right? And in fact, that was an FDA approved outcome for approving drugs. And it turns out the reason that worked well is that if your creatinine doubles versus stays the same, basically you have a 57% decline in GFR and about a 30-fold higher risk of ESRD. On the other hand, here in the prevalence in the middle panel, you see that only 0.5% of patients with CKD have something that bad happen to them over the course of 2 years. So then what we did was said, well, what about a lower decline, like 30%? And you'll see that it's more patients, and it's still associated with a 5-fold higher risk of ESRD. So we can say that really any decline is associated with risk. The confidence intervals in the shaded region are very tight. But by the time you get to a 30% decline, you really have substantial increased risk, and you've gone enough of a road that it's of concern. And you'll see that it's actually consistent in the greater than GFR 60, but of course declining 30% from 100 is all the way down to 70, whereas declining 30% from 50 is just declining by 15. So it might happen a little more rapidly. Also here you can see that plus or minus 30% for GFR is actually the majority of the people, but there are a good number of people who progress more rapidly than that, and there's this fraction of people who seem to have a rise that's bigger than that. So we're not really sure, and I think some of the people who have a 30% decline have real decline, and a few of them may go back and have a little bit less as well. We also can see that by moving from a doubling of serum creatinine to just a 30%, we capture a lot more people and a lot more of the risk, right? So if we waited for creatinine to doubling, we're really waiting too late and telling people once they're almost at ESRD. And also for drug development, it's nice to have earlier outcomes. In terms of consistency across the studies, I told you that there was about a 5-fold and 6-fold greater risk of ESRD once you had a 30% decline in 2 years. It is remarkably consistent across all the studies we looked at, right? The studies really line up along the line and quite consistent at the high end as well. So we really think this is a robust conclusion throughout the globe. We also looked at this in a broader context in a series of articles, both in a summary written up very nicely by Dr. Levy and the whole group, and commentaries by the FDA and EMA as to how it relates to trials. And basically, we looked at the trials, and this is led by Leslie Inker and Hito Hirschspring. And what they've seen is that in trials, if you look at the hazard ratio for the established endpoint, which was doubling of serum creatinine or ESRD, and you look at it for the alternative endpoint of a 40% decline or 30% decline, if you had a 40% decline, studies that had a more likely or were therapies that were more protective for the 40% decline were also more protective for ESRD. But you'll see that the confidence intervals are really very wide. So the ability to look at this correlation, it's very supportive that the two are similar, but it was helpful to be able to add a lot of observational data. And you can see that for 30% decline, it's again supportive, but there's a lot of variability. I think the other important issue is the issue of an acute effect, right? And this is a summary from that paper. I won't go through all the details, but if there's no acute effect, then really 30 and 40% decline is a very good outcome in terms of progression. What we worry about is if there's a small or a large positive or negative. In this case, things like ACE inhibitors may have a small negative acute effect. So basically, hemodynamically, you're basically lowering the filtration, but we think it's protective because you're basically lowering the pressure across the glomerulus, right? But if that happens, DFI dips a little, and then it's easier to cross to a 30% decline, right? So in that case, you really may get to type 1 errors that are not acceptable and get false positives for harm, where it may appear that a therapy is harmful, but it may actually be protecting the kidney a little bit, and 30% is not so far away from whatever it was that happened acutely. So this issue of no acute effects is an important caveat for progression based on eGFR. So if you think that something else happened, that really is a modifier for being able to assess progression, and maybe you need to get to an interval where you didn't have major changes that had acute hemodynamic effects on GFR. And the review paper sort of describes that in a lot more detail. Basically, the summary of that evidence is that based on a series of meta-analyses of cohorts, clinical trials, and simulations of trial design, we suggested that a confirmed decline, and what we mean by confirmed is once you get to a 30% decline, checking that it happens in 2 serum creatinines, 2 estimated GFRs gives you more confidence and less false positives. Over 2 to 3 years may be an acceptable surrogate endpoints for drug approval, and I think also looking at things clinically and saying that things have actually gotten worse. But you need to specifically look at acute effects, and there are some other caveats that are worth taking into account. What about that other picture, which I called the clinical perspective, right? In some sense, let's draw this distinction. You say, well, I showed you that this patient B is worse than patient A if you compare them back here. But if you're already knowing that patient B got to here, then you may want to say, well, what about at this point? Is this patient B worse off than somebody who was just stable at 45 all along? Can I extrapolate clinically when I see the patient and I already know that they progressed based on the past, right? So the question is, how powerful is extrapolation of past rapid progression into the future? And basically, what we do there is we've done the same type analysis. We looked at it as slope because we think clinicians sort of think about that extrapolation more as a slope. And we're going to compare patients who've had a decline either in the high risk, in the high GFR from 96 to 74 or in CKD from 61 to 42 versus other people who are on average stayed at 53 and see how much worse off are these patients, right? And basically, we have lots of ESRD events. And if we look at this risk, and that's been published as well, with Csaba Kövesdi as the lead author, basically, if you have a slope of -6, your relative hazard is 2. And if your slope of -3, your relative risk is 1.7 compared to no progression. And if you did that over 3 years, that's more indicative than 2 years. And slopes over 1 year are actually very difficult to extrapolate. So I do think you should be cautious in that in a meta-analysis we can see a difference, but these relative hazards are now 1.3, much smaller. So this shows that the result is consistent across multiple studies. And now to compare the various perspectives, I think one of the sort of humbling things is that current GFR, if you just have a current GFR of 30 versus 50, your ESRD risk is about 20-fold, right? Now, we want to be clever and say, what if you had a decline from 50 to 30 versus somebody else who stays at 50? And it turns out that decline of 40% gives you a relative hazard of about 10, right? So if you start at one person goes to 30, you really know that person is worse off, and you have to be worried about what happened. On the other hand, if you really want to be clever and say you've got 2 people who are at 32, but one of them came from 50, they've had rapid decline in the past, whereas the other one stayed at 32 for a period of 3 years, it's actually a slope of -6, very similar. Your ability to extrapolate for the 2 people who are standing in the same place is only a 2-fold relative hazard, right? So there's lots of information, but it turns out the cross-sectional picture has an incredible amount of information. And the ability to amplify it, you can amplify it depending by about 2-fold more to extrapolate, right? And this kind of shows you what that looks like by GFR slope and by baseline GFR. And the thing is, you'll notice if your baseline GFR is low, then the risk is much higher, and the lower slope of -6 gives you a much bigger gradient versus no progression. Whereas if you start out at 50, you really are a long way to ESRD, so your 3-year risk of ESRD stays pretty low. You may need to get to a 10-year horizon or a 20-year horizon. So the time horizons are also very important. Next, and before I conclude, I wanted to talk about ACR change. We're really working on this intensively for a 2018 meeting to think very carefully about when that can be used in trials, and we all know that that's been very promising but also potentially problematic. So we've looked at ACR fold change and future risk of ESRD. And this is a leading publication by Juan Jesus Carrero from a 1 million-person database where they culled the subset with change in albuminuria in the Stockholm study, abbreviated SCREAM. And you can see that the ACR change here, a lot of the people are between 4-fold increase and 4-fold decrease. So there's a fair amount of variation. The increase or decrease is strongly associated with ESRD risk. So a fourfold decrease is about associated with a threefold lower risk of ESRD, and a fourfold increase the opposite. The mortality association was a little more complicated. This was also consistent in a lot of subgroups, and we're going to look at that for consistency in terms of being able to generalize the results. Right? This is stratified by diabetes, which is one of the most important subgroups, and you'll actually see that the risk association is every bit as strong in non-diabetics as diabetics. Right? But this is a fold change, and in the non-diabetics, it may be a lower level of albuminuria. We also looked at subgroups, and it's very consistent across subgroups, including the subgroups of those not using ACE inhibitors, using ACE inhibitors, and starting or stopping ACE inhibitors. So we're actually able to start looking at robustness across a wide range of groups. So my final slide in terms of conclusions for progression are meaningful CKD progression can be understood in the context of its prediction of future risk. There are two different perspectives. The clinical trial perspective, if progression will happen, will it predict subsequent risk? And that adjusts for the first measurement. There's the clinician perspective. Does past progression predict future risk? And there you're adjusting for the last time point because the clinician's already seen the patient at that last time point and knows whether they've progressed in the past. An eGFR decline of about 30% is associated with fivefold higher risk of ESRD, and confirmation with a second serum creatinine and eGFR is good, and thinking about acute hemodynamic effects can alter the meaning of the decline in GFR. Albuminuria is variable, but large changes are clearly informative, right? And this is in the context of health systems where we know the measurements aren't perfect, right? If the methods were better, we might have better results. And as a surrogate, ACR speaks only to efficacy and not safety. So if you're going to approve a drug based on a one-year study, you better pay attention to the long-term safety separately. And in terms of the clinician perspective, adjusted for the last visit, past GFR decline is moderately predictive. A slope of -6 mL per minute per year for 3 years was associated with a twofold higher risk of ESRD. And you have to remember that the current GFR is incredibly predictive, but over a much wider range. So in some sense, this is very useful, but it has to be nuanced when you have one patient. And then the current ACR probably includes, I think, most of the information in ACR. So I haven't shown you that data, but I think like blood pressure, when you get to the final level, that level of ACR may be the thing that's quite predictive rather than remembering your entire trajectory of previous ACR. So I have to acknowledge many, many people. These are very large teams that have entrusted our data to us, the CKD EPI collaboration, the CKD prognosis collaboration, international groups, and thank you very much for your attention.
So the session is open for questions. Could I ask, in the meantime, something? So do you think the combination of ACR and eGFR together would allow us to have shorter periods of follow-up, or do you think we still need 2 years and 30% decline with or with CR?
Yeah, I think your intuition is correct. We're trying to develop the numbers for that, right? I mean, clearly albuminuria changes themselves happen relatively fast, within months. So that is great. Then I think what we need to develop are the standards for how many measures we really need to be able to say things with confidence about people. Unfortunately, in many of our large clinical studies, we only have one measure and then another measure a year later. It may be if you really want to know what happened to a therapy, you may need like 2 measures, the therapy, and then 2 more measures. I don't think that we'll be able to use the GFR slope itself for periods under a year, right? Because realistically, rapid progression may be 6 mLs, 5 mLs, slow progression is 2 mLs, so the difference is 4 mLs, and that variability is just unrealistic. So I think maybe in the short term, we might use GFR to look at avoiding AKI, and then once you get to a few years, we might be able to combine it more meaningfully. But it is a nice idea, which we're going to try and explore.
Thank you. So our next speaker is Ariela Benigni. She's from the Mario Negri Institute for Pharmacological Research in Italy. She's the head of the Department of Molecular Medicine and Scientific Secretary of the Mario Negri Institute for Pharmacological Research in Bergamo. She's considered one of the top Italian scientists. Thank you, Dr. Benigni. She will speak about what drives CKD progression.
Thank you. Thank you, Dr. Madero. I'm very pleased today to be here to show and share with you some recent data we had in the lab in the area of chronic kidney disease progression. The discovery by Dr. Brenner and his co-workers that disease progression were fostered by glomerular hypertension. How can I is there a pointer? Yeah. The mouse. Thank you. Okay, thank you. That disease progression can be fostered by glomerular hypertension prompt us to try to unravel possible mechanisms linking glomerular hypertension to disease progression. And early studies have shown that glomerular hypertension imposes mechanical strain on glomerular podocytes, enhancing the power of the glomerular pores dimensions as to increase the protein traffic throughout the glomerulus and resulting in proteinuria. Proteins filtered in exuberant amount are actively resorbed by, accumulate first in the proximal tubule and actively resorbed by proximal tubular cells. But these cells are not created to resorb such an amount of proteins and high amount of proteins, and they undergo apoptosis, leading to glomerular tubular disconnection and phenotypic changes. The character of such phenotypic changes were studied by a number of scientists, including us, and after exposure of proximal tubular cells in culture or excess proteins, and these authors, including ours, invariably detected an FKB activation after reactive oxygen species generation and production of vasoactive and inflammatory mediators encoded by genes that were NF-κB dependent. The link between protein traffic and NF-κB activation in vivo is offered by these studies by us many years ago, showing that in renal mass reduction rate, proteinuric model, the progressive increase in proteinuria is accompanied by progressive activation of NF-κB, and more importantly, when ACE inhibitors were given to these animals, this treatment reduces urinary protein traffic and completely switch off NF-κB activation. Within the proteins filtered during the disease, chronic kidney disease, albumin is the one that induces NF-κB, as documented by these studies, showing that nuclei from proximal tubular cells exposed to albumin were stained by P65 and P50, that are the subunits that are formed during NF-κB activation. As you can see, as little as 2.5 albumin milligram per milliliter was capable to significantly enhance NF-κB activation. So the albumin itself is capable to activate NF-κB and let the production of RANTES, MCP1, all these vasoactive and inflammatory mediators, and in the basolateral compartment of these cells. So if these were to occur in vivo, we may understand that these mediators can be released into the intestine, where they can attract inflammatory and immune cells and can stimulate the production of extracellular matrix by resident fibroblasts, leading to fibrosis. We know that among the factors, NF-kappa-B-dependent factors, TGF-beta is a main instigator of fibrosis, and it does it through the activation of SMAD3 that is capable to inhibit antifibrotic miRNA, microRNAs, and promote the generation of profibrotic microRNAs. MicroRNAs, all of you know, that are short non-coding RNAs that regulate gene expression through transcriptional and epigenetic mechanisms. They affect several processes from development to disease condition. So a few years ago, we were interested to see whether the transcription regulation by microRNA could have a role in the development of fibrosis of a particular strain of rats, the Munich Vista frontier rats, that spontaneously develop proteinuria and glomerulosclerosis with time. And since glomerular dysfunction is one of the main features of overproteinuria, we took the microdissected glomerula of these rats and assessed the microRNA profiling. Among all the microRNA that we observed, 1/3 was differentially expressed. And these are the 10 mostly upregulated microRNA with relative fold changes. And you can see the microRNA 324, 3P was the most upregulated. We confirmed this data with the PCR, real-time PCR, and indeed this microRNA was increased in MVF rats in respect to Vista rats. With in situ hybridization, we could localize the microRNA that was expressed in some podocytes and in parietal epithelial cells of the Bowman capsule, but more importantly in cortical tubules. With an in silico approach that is data search for a target using bioinformatic tools, we found 95 transcripts that could be a target of the microRNA 324, 3P. And within these targets, we choose prolyl endopeptidase, that is a serine endopeptidase that digests angiotensin 1 and 2 into angiotensin 1,7. That is well known to counteract all the deleterious effect of angiotensin 2. The endopeptidase was also capable to generate an antifibrotic peptide from thymosin BT4. We next evaluated the expression of microRNA is target and correlated them with fibrosis. As you can see, particularly in Munich Vista frontier rats at an advanced stage of the disease, we found that the tubuli were robustly expressing microRNA, and these same tubuli, because these are cellular sections, were consistently negative for the target PrEP, and this was associated in much more fibrosis evaluated as use red. When we treated animals with lisinopril, there was a downregulation of the microRNA, preservation of the target, the PrEP, and amelioration of renal interstitial fibrosis. And this was accompanied by more ACD STKP peptide, the antifibrotic peptide, that was increased by lisinopril. So all these data concur to indicate that this microRNA and target pathway can have a role in fibrosis, in chronic renal disease, proteinuric, non-diabetic. We then move to a more closely to the clinical condition, more closely model to the clinical condition, that is Zucker diabetes fatty rats. And with the similar approach that we had with Munich Vista frontier rats, we found that there was one microRNA 184 that were consistent and robustly upregulated 23-fold in diabetic rats in respect to controls. And this was expressed mainly in proximal and distal tubules as a colocalizes with aquaporin-1 and tamorsal proteins. We searched for the target, and the target was lipid phosphate phosphatase 3. This is a membrane glycoprotein highly expressed in the kidney that catalyzes this phosphorylation of lipid phosphates and has a role in some processes, deleterious processes, pathological processes, including fibrosis. And again, we evaluated the expression of mRNA in the diabetic kidney and found an increased upregulation in tubula, and this is accompanied in the serial section of downregulation of its target, and this was associated with increased deposition of type 3 collagen. So what drives the expression of microRNA 184? We evaluated different pathological stimuli, angiotensin II, albumin, transferrin, and TGF-beta, and found that among these stimuli, the most effective in inducing the microRNA expression was albumin. How can it be possible? Let's consider which are the epigenetic changes that that regulate gene expression and gene transcription, and allow to switch from a DNA silent compact state to an active loosey state of the DNA. Here you have, in control condition, the chromatin is tightly bound to DNA, and there is an increase in DNA methylation, histone methylation, chromatin condensation, and in this condition, the transcription repressors, such as methyl cytosyl protein binding 2, is tightly bound to the DNA, as you can see here. When gene is activated, there is a decrease in DNA and histone methylation and reduction in transcription repression binding, an increase in histone acetylation, and this allows the chromatin to open and to leave the possibility to have transcription factors that can bind to this DNA. So through computational analysis of the rat genomic region surrounding the miR184 gene, we identified different regions. A CPG island region, which is very prone to the binding of transcription repressor, and a region upstream the transcriptional site of the miR184 gene, which is susceptible to acetylation, and NF-κB dependent binding domain. After exposure of proximal tubular cells to albumin, we found that in the nuclei of these cells, albumin was capable to reduce the binding of transcriptional repressor, to increase the acetylation, histone acetylation, and to induce NF-κB activation. And this cartoon summarizes these facts. So albumin, through the reduction of the MACP2 binding and increase histone acetyl, may allow P65, which is this subunit of NF-κB, activated NF-κB, to transcribe the gene of miR184, reducing LPP3 and induce fibrosis. Through PI1, I had no time to tell you why, but believe me, this is the major instigator in this model of fibrosis. So the confirmation of what we have seen in vitro, in vivo, was that if we treated diabetic animals with ACE inhibitors, we reduced albuminuria, reduced the expression of miR184, and preserved PrEP expression in respect to untreated animals, and ameliorated tubulointerstitial damage. But last but not least, albumin can contribute to fibrosis also because it is a source of antigenic peptides. And a few years ago, we found that, first of all, as I told you, albumin is capable to induce NF-κB-dependent genes, and the resulting proteins are secreted towards the interstitium where they can attract immune cells like dendritic cells. But in the same time, proximal tubular cells can digest albumin into smaller peptides. Here are the mass spec profiles, and you can see albumin 124 is the major product of the digestion, which is taken up by dendritic cells that further digest this albumin into smaller peptides of the size of the grove of MHC class 1, and when dendritic cells traffic from the kidney to lymph nodes, they presented into the MHC class 1 grove these peptides to CD8 positive T cells that are primed, and when they are primed, they return to the kidney and to the renal tissue, and engages and instigate inflammation. And that's why we found, either in experimental animals or in patients, some CD8 positive cells surrounding the tubuli in proteinuric conditions. So, in conclusion, many studies from our labs in the last few years have consistently documented that albumin is a major instigator of inflammation and fibrosis. And it does so through NF-κB activation and epigenetic regulation. And also, it is also capable to form antigenic peptides that contribute to fibrosis with promoting an immune reaction. Thank you very much for your attention.
Well, thank you for a wonderful presentation, Professor Benini. The session is open for questions to Professor Benini. Yes, go ahead.
Thank you. I'm David Packham, Melbourne. Thank you for your lovely presentation. I wonder if you'd comment on renal fibrosis in the analbuminuric rat.
Analbuminuric rat.
Yeah.
Yes, of course. What I have showed to you are data in proteinuric conditions. So if you have proteinuria is a major instigator. Of course, you are right. There are cases in which you don't have proteinuria, you have fibrosis. And in this case, of course, the instigators may be others, like angiotensin II, for example. In this particular model I showed to you, angiotensin II was not effective, but in general, angiotensin II promotes fibrosis. Thank you, David.
I wonder if I might ask a question. Although this gets into the clinical realm, how good or how high does the albumin in the urine, do you think, have to be in order to promote this kind of injury? Do we need to be concerned about levels of albumin that are very low, only very high, or is there, do you think the urinary albumin is a good measure of the damage that's occurring?
Yes, it's a very good point. It's very difficult to answer to. We know that also microalbuminuria in diabetic patients can drive progression of kidney disease. So I don't think it's a question of how much albumin you find in the urine, but how long this protein traffic occurs in the kidney. Because if the exposure of proximal tubular cells to albumin and also to podocytes, I didn't show it to you, but of renal cells to albumin for a long period of time, even at very low level, it induces such detrimental effects.
May I ask another question?
Please.
Do you think the other filtered proteins are damaging? For instance, if the glomerulus is very leaky, we have higher molecular weight proteins that are filtered. We also have lower molecular weight proteins.
Yes. You are right. We are currently studying different proteins, and particularly complement components that are filtered in exuberant amount also with albumin and IgG can be detrimental, particularly because these proteins not only affect tubular cells, but also they affect the podocyte behavior. So they derange completely these. If you expose podocyte in culture to C3, for example, C3A, which is a byproduct of degradation of C3, you have actin reorganization, active cytoskeleton reorganization, reduction of nephrin. So some detrimental effects are driven also by complement components. And IgG may also have a role. Although albumin, within IgG and albumin is much more toxic, let's say.
Well, thank you very much. The next speaker is Professor Tazeen Jafar. Dr. Jafar is Professor of Health Services and Systems Research at Duke National University of Singapore Graduate Medical School and visiting consultant at the Renal Medicine at Singapore General Hospital. By the way, our speakers have much longer introductions than we can give, but we thought you'd rather hear from them than from us about them. So, Dr. Jafar, we're happy to hear your presentation.
Thank you. So thank you. The title of my talk is Public Health Interventions for Delaying Progression of Kidney Disease Globally. So let's move on. Yeah, okay, thank you. Disclosures. So chronic kidney disease has become one of the leading and, in fact, the most rapidly rising cause of death globally. In fact, it has risen up almost 80 percentage points as a cause of death over the last 2 decades. These are data from the Global Burden of Disease 2015, showing 8 standardized death rates from CKD and also the attributable risk factors. And as you can see, systolic blood pressure and high blood glucose are now one of the leading attributable risk factors in pretty much all regions of the world. So these are the World Bank regions. So all regions of the world, as is high BMI or overweight or obesity, and therefore these must be addressed. Now, dialysis continues to be expensive, not just in the high-income countries, such as the US, where it consumes more than 7% of the US Medicare budget, but also in low and middle-income countries. These are data from a recent systematic review. And in countries such as India, Nigeria, the annual cost of dialysis from a payer's perspective is as high as almost $40,000 corrected for international purchasing power parity. China, something like $35,000. So this is completely out of reach for people in low and middle income countries where, despite the fact that these countries have made considerable economic progress, and the vast majority of the population still lives in many low-income countries, still living in the slums, still living in conditions of poverty. Poverty head counts are high. In Nigeria, for example, more than 50% of the population still living less than $2 per day. Even in India, 58% of the population, according to the World Bank, still living less than $3 per day. And so a nice systematic review published a couple of years back in The Lancet by the George Institute showing more than 90% of the people living in low-income, low and middle-income countries are not, who need dialysis and renal replacement therapy, are not able to access it. And so unfortunately just die from lack of access. And kidney transplants are also, kidneys are just not available because of lack of donors, a lot of cultural reasons, and also logistical issues. So transplantation not a viable option. And therefore prevention of incident kidney disease and progression of kidney disease is very important in high-income countries and more so perhaps in low and middle-income countries. And so let's be talking about prevention. What would be the optimal public health approach for prevention? We'll obviously need very strong policy action, strong health systems interventions, and community mobilization. All of this to be acting together. right? And so, and for implementation of these strategies, and these strategies, there are several strategies that have been shown to be effective and efficacious. There are loads of trials data now. I don't have the time to go into the details beyond the scope of the talk today to show you all the trials data, but lots of them that have been shown to be effective in preventing kidney disease and in preventing cardiovascular disease. So implementation of those strategies is vital, and like I said, all of these need to be done together. And so, and these health system strategies include identification, screening, and identification of individuals who are at high risk, and then implementation, the strategies to keep people here on the left, keeping them healthy and on the left of this chain of progression of kidney disease. So that is the goal. And so screening of people for proteinuria and then implementation of these strategies have been shown to be cost effective using the threshold of 80,000 per quality adjusted life year saved. Now this threshold of 80,000 per quality saved is based on the WHO standard for high income countries, which is 3 times the GDP per quality saved. And using this threshold, screening for proteinuria has been shown to be cost effective for people with hypertension, for people with diabetes, and in the general population, we've had mixed results. So if a general population is kind of a very low-risk population, then it's not cost-effective. However, if the general population is a little bit higher-risk population with a high incidence, a high progression, or high prevalence, then it probably is going to be cost-effective, which is what the Japanese data have shown. Likewise, for screening cost-effectiveness for EGFR, there are not many studies done, but a Canadian study has shown that it is cost-effective for people with diabetes in the elderly population. And then there is Japanese data showing that mass screening of EGFR annually is cost-effective. And when you couple it with proteinuria, it is still cost-effective. And again, this is a little bit higher risk population, but it is cost-effective. And these strategies, screening for albuminuria, screening for EGFR, have been implemented in a number of programs, so which is integrated in their not-for-profit program, in the public health sector, in the US, in the UK. All of this started in the early 2000s. So the Kaiser Permanente system, the VA system, and minority populations in the US, in the UK, in the National Health, NHS. And in the UK, we've even piggybacked a pay-for-performance mechanism within this, so rewarding the providers for establishing CKD registries and rewarding them for starting ACE-ARB therapies. In Canada and the First Nations communities, the CKD program in Australia and New Zealand, in Taiwan and the Japan with the mass screening. So all of these programs are all integrated programs for targeted screening for hypertension, diabetes, and they've all reported success, which is based on referrals and the patients really reaching quality indicators and delayed time to renal replacement therapy as compared to national average. Now, these are not randomized trials, but still, compared to the national averages, this is all movement in the right direction. Now, another key component that these programs are shared has been an electronic information technology system, automated reporting of EGFR, which is a key element in pretty much all of these programs, and establishing clinical registries and a strong clinical decision support system, which must be encouraged in all the programs. And so what has been observed in the US and in a number of industrialized countries which establish programs like this is that the rate of age-adjusted rate for end-stage kidney disease has now started to decline. So up until 2000, they were increasing. Since 2006, there was a plateau. And since 2006, there has been a decline in the age-adjusted rate for end-stage kidney disease. And very recently now, we've seen that the rate for prevalent CKD stage 3 and 4, the age-adjusted rate, have started to plateau in the US, and also probably in the UK and other industrialized countries. So this is all things moving in the right direction. Now, what has also happened concomitantly, if you look at the NHANES data between 2002 to 2010, treatments have improved, right? So use of antihypertensive medications improved, blood pressure control doubled, ASR use have increased substantially, glycemic control. So all of these treatments improved. And the other thing that happened is the automated reporting of eGFR. Of course, Dr. Levy's efforts were instrumental in that. So that happened in early 2004 and has gone pretty national here and also in the UK and in other industrialized countries. And obesity prevalence, diabetes prevalence, and hypertension prevalence has plateaued, indicating that the risk factors have actually gone down. Some policy level efforts, behaviors, lifestyles have improved. So this is again a concerted effort, some policy level efforts, and definitely treatments. And the impact of that. Now, what is happening in the developing country is actually, so while not so good. So while we are seeing that hypertension rates are improving in high-income countries, the reverse is happening in low and middle-income countries. Age standardized prevalence of hypertension is increasing. Age standardized rates of diabetes are in fact going up. Not just that, the unawareness rates are abysmally poor. More than 50% of the population with hypertension are unaware. 50% of the population with diabetes are unaware. So then the question of how can we replicate the same thing in low and middle income countries, that's going to be very challenging. So if you just screen the people with hypertension and diabetes, if half of them are not even aware, it's not going to be a cost-effective program in that setting. So that's going to create new challenges. So the first step in a low and middle income country settings would be to screen for hypertension, to screen for diabetes, and then screen for CKD. And in many of these countries, there isn't a hypertension program, there isn't a diabetes, there just isn't a non-communicable disease infrastructure to piggyback CKD on. There are maternal child health infrastructures, there are infectious disease infrastructures. So that's the infrastructure that one has to take advantage of. So, and that's what we did in the control of blood pressure and risk attenuation trial as an example, where, for example, there's these, and in many developing countries, there are these community health workers who go door to door and deliver maternal and child care services and vaccines. And we trained these community health workers in what we call home health education, which was health promotion efforts for hypertension care, teaching the individuals on strategies such as low salt diet, increasing fruit and vegetable consumption, smoking cessation, maintaining ideal body weight, increasing physical activity, using behavior change communication strategies. This was a randomized control trial, and general practitioners in the same communities in updated management of hypertension. So the one group was the combined strategies, single strategies, and then usual care was no intervention. And we measured their estimated GFR. This was the CKD-EPI GFR validated for the Pakistani population. And what we observed at the end of 7 years, so these interventions were delivered over 2 years, and then we measured eGFR at baseline, and then at 7 years, so 5 years after the cessation of intervention. And what we observed was from baseline to 7 years, there was no change in eGFR in the group that received the combined intervention, but eGFR declined in the usual care group, and this was a statistically significant difference. We did generalized estimation equation accounting for all the baseline characteristics and the differences in blood pressure, but the conclusion was the eGFR was preserved with the combined intervention. So what the conclusion is clearly that task shifting to community health workers and low-cost strategies are probably are effective, and this model can be improved considerably and things can be added on, but this is a workable model for low and middle income countries as a health strategy platform. And a key facilitator that I must say in this model was access to high quality, low cost antihypertensive medication. I'm going to come back to this. We also assessed the cost effectiveness of this model for CVD dialysis averted, and it was highly cost effective. From a variety of perspectives. It was also affordable, which is something that I do want to mention again, because strategies not only have for low and middle income countries, not only have to be cost effective, they also have to be affordable because they're competing with other programs like a malaria control program, like a diarrhea control program. Tomorrow is the World Malaria Day. 43% of the population in sub-Saharan Africa is at risk for malaria. So, how do you go and advocate a CKD control program? So you have to compete with that. So you have to think about piggybacking it or resource sharing somehow. So that's an important point. But this model of task shifting and using the existing workforce of community health workers is replicable in other settings. For example, in India, India has these ASHAs. Their community health workers are called accredited social health activists, and there are about 900,000 ASHAs in India. And in the National Health Mission, they have just started a program for universal screening of diabetes and cardiovascular disease. It's being piloted in 30 districts in India, and it will soon go completely nationwide. This is an excellent program to piggyback CKD screening on. We've just started a pilot study in India with the George Institute for piggybacking CKD